So logarithmic functions are what I would consider to be probably the second most difficult of all of your core functions after inverse trigonometric functions. Largely because the concept of logarithms is quite difficult, full stop, and it's related to inverse functions, which are hard as well. So let's recall the basics of logarithms. So if I have a function which is an exponential function, so this is 1 to 1. So maybe I should just say, when I'm talking about exponential functions, let's assume, so we've got to be very careful here. So this is an exponential function. And let's assume, of course, in an exponential function, you want b to be strictly greater than 0. Otherwise, you have awful problems taking things like square roots of negatives. And let's assume b is not equal to 1. Because if b is equal to 1, this is just the constant function 1. So we saw, when looking at exponential functions, that this thing is 1 to 1. It's either always increasing or always decreasing. So 1 to 1. So that means it has to have an inverse function. So this implies there is an inverse function. So what is the inverse function? Well, let's recall the defining property of logarithms. So let me remind us what a logarithm is. So the defining property of logarithms was the following. Log to the base b of x is equal to y. This is exactly the statement that b to the y is equal to x. It's exactly that statement. Okay, this is the meaning of logarithms. So I think I wrote this last time with kind of x is equal to a and y is equal to c. At least that's when I was doing it before. But that's because I was only just thinking about the raw definition of logarithms. I wasn't thinking about functions at the time. And again, let's be careful. What's this x in? This x can be anything in 0 to infinity. And this y can be just anything at all. Okay. So let's remember the definition of an inverse function, shall we? So recall again, if I have a function f, what's the defining property of the inverse function? The defining property of the inverse function is the following. F to the minus 1x is equal to y if and only if fy is equal to x. Right, that's the meaning of an inverse function. That's the meaning of the inverse function. And look at what we've got. We have exactly that, where f is my exponential function here, with base b. So the conclusion is the following. By definition, if you want, the logarithm function is the inverse of the exponential function. That's the meaning of it. So when I wrote this down before, really I was writing the definition of the inverse to the exponential, but I wasn't calling it that at the time. So the conclusion is log b of x. So this is a totally reasonable function now because b is fixed and x is like a variable. Different values for given inputs. This is the inverse function. To b to the x. That's what the conclusion is. The defining property of the logarithm, this first red box I've written, is literally the statement that the logarithm is the inverse function to b to the x. And again, let's just make sure we understand this is only going to work. This is only going to work if b is greater than 0 and not equal to 1, because you're not 1 to 1 if you're equal to 1. So that's a really useful thing to know, because we know quite a bit about inverse functions. We know how to graph them, for example. And we know lots of properties of exponential functions. So I think we can use those basically to get some feel for the properties of an or a logarithmic function. So let's do that. So let's do properties of f of x is equal to log sub bx. So maybe I won't use f of x, just because I've used it already for my exponential function. Not a huge deal, but let's just do this. So properties, and maybe again, let's just make sure we understand. This is not just properties of the logarithm I was talking about. So in the logarithm videos, we thought about the algebraic properties of logarithms, things like that, log laws and that kind of thing. This is a little bit different. I'm thinking about the function here. So I'm trying to understand how log b x depends on x, essentially. And again, let's make a convention here, because I could do this for any b strictly greater than 0, not equal to 1. But let's assume in everything I'm going to do that b is strictly bigger than 1. The reason for this is when b is between these two is really not used. Isn't used often. Overwhelmingly, you're going to find that the logarithm function that you're going to study in calculus, there are going to be two. One is going to be log base 10, kind of for obvious reasons because of our decimal system. But there'll be another base as well, which will be more important than that, which is something you're going to study when you kind of first start doing calculus. But I want to kind of get the basic idea. And both of those bases I'm talking about are strictly bigger than 1. So there's no point really in doing a completely general story. So I'm only going to focus on this case. So let's do the graph first. So the graph looks like the following. Of all things you should know about logarithm functions, having a clear picture in your mind of the graph is, I would say, probably the most important, because you can discern so much from the graph. So this is what it looks like. Kind of a rather interesting looking graph. So it's got this kind of strange behavior where as I get closer to 0 it gets really big and negative, a little bit like an infinite discontinuity when we're thinking about rational functions. Well, I'm crossing here, and that's actually at the point 1. So this is the graph y is equal to log to the base bx. Why is that the case? It's because b to the 0 is equal to 1, so log to the base b of 1 is equal to 0. Now, why is this the graph? I think it's important you understand this, because it might be hard to remember this graph. So remember, this is the inverse. This is the inverse to the function b to the x. And we know what the graph of b to the x is. It's going to be, because it's strictly bigger than 1, it's going to be this exponential increasing graph. So it's an inverse, so it's a reflection in the line y equals x. So this is a reflection, or I should say the reflection. There's only one. The reflection in y is equal x of the graph y is equal to b to the x. Remember, that's how we define, or that's how we graph an inverse. So let me just talk us through this carefully. So if I graph this line y equals x, I'll do it like this. So we looked at this in the video on inverses, or the second video on inverses, I think. So was it the second? One of the two videos. So if I was to graph y is equal to b to the x, it's going to look like this. So this is y is equal to b to the x. I'm assuming it's strictly bigger than 1, b is strictly bigger than 1, so it's going up like that. Well, the reflection is the reflection across this, so that's the reason it looks like this. So we're reflecting across this. That's what's happening here. Very nice. So I would really strongly recommend that's how you remember this, because the exponential function, the shape of that is something which is very natural. We've kind of it turns up so often. Logarithms are like, well, this is a weird inverse function, but thankfully it's just the inverse, right? So that means it's a reflection across the x-axis, or this straight line y equals x. Essentially because it's flipping the inputs and outputs, and doing this reflection changes the x and the y coordinates, as we saw. All right, so from this we can determine a huge amount of stuff. So we can read off things like range, domain, all that kind of thing. And we know these anyway because we know the ranges and domains of the exponential, so they all kind of follow. So the domain, what's that? Well, that's all possible inputs. Everything's strictly greater than 0. And if you want to compare this to the inverse, so this is because, well, remember what inverses do, it flips domains and ranges. This is because the range of b to the x is 0 to infinity. Okay, so that's a nice way to think about it, because the inverse, if it exists, flips it. Same thing with ranges. So the range now, you can kind of see it from the picture, it's all possible y's are hit. So the range is minus infinity to infinity. And again, this is because the domain of its inverse. That's the reason. Next, increasing, decreasing. Well, we can definitely see it's increasing from the picture. So it's increasing on its whole domain. We don't need to do any weird restrictions or anything like that. So let's do an example of this. Kind of a more algebraic type example that we saw in the algebraic videos. So imagine I want to find the following. So find, let's say, x such that, okay, here's a good one. We'll do 2 to the power x minus 1 is strictly less than 8. Okay, so what do I know? Well, of course, it's an exponential, so it's always going to be positive. So we've got 2 to the x minus 1 less than 8 here. So now log is an increasing function. So that means if I do logarithm of both sides, ignoring the 0, that's just there to make sure we understand we can apply logarithm, then I get, it preserves the inequality. So if you remember, one of my properties of inequalities, what logarithms preserve them, that's exactly the statement that, or at least they preserve them if the base is strictly bigger than 1. That's going to be exactly the statement here, that log. So let's do log to the base 2, because the 2 there is a sensible plan. We could do it in another base 2, but this is a nice plan. 2x minus 1 is strictly less log to the base 2 of 8. Okay, so this is, from our perspective now, the fact that logarithm is an increasing. So log to the base 2 is increasing, because 2 is strictly bigger than 1. If 2 is between 0 and 1, it's actually decreasing. And again, that was covered carefully when we were doing algebra with inequalities. So what does this tell us? Well, at this point, it's maybe worth pointing out that this is equal to 2 to the 3 So by definition, basically, this implies that x minus 1 is strictly less, what am I doing? It's x minus 1 is strictly less than 3, by definition of what a logarithm is. So this implies x is strictly less than 4. So we could write that in interval notation. I'm not going to bother. Next, even, odd, neither. Definitely not. Can't be either. Has neither of the symmetries that we're looking for. We can't feed in negatives, it's the main problem. So neither, odd nor even. And I mean, both are impossible, as I say, because the domain is only positive numbers. And for an even or an odd function, if x is in the domain, minus x has to be in the domain. Finally, well, let's do 2 more. So actually, no, I should maybe, let me do it up here. That makes more sense to talk about what am I going to say now. So first of all, bounded, unbounded. It's unbounded there. And as we can see, there's only one x-intercept at 1. So I'll just put this in here because it's kind of a logical place to put it. Log to the base b of x is equal to 0 if and only if x is equal to b to the 0, which is equal to 1. So there's only one x-intercept corresponding to the y-intercept over here for the exponential function. So the last thing I'll say then is it's 1-to-1. Of course it's 1-to-1. It has to be 1-to-1 because it's itself got an inverse. The inverse of an inverse is just the original function. So this is with inverse. With inverse b to the x. So logarithms as functions are not too fearsome really, right? They look like this. You can read off all the properties of them basically from these graphs. We're assuming here that b is strictly bigger than 1. If b wasn't strictly bigger than 1, we'd have a kind of a different situation, largely because the exponential function would look so different. So let me just very, very quickly write this down to illustrate what I mean. If I had an exponential function which was b strictly between 0 and 1, this is what the exponential function, so can I get it reasonable? The exponential function would be kind of the mirror image of this one in the y-axis. So that picture is where I have, whoa, can I wrap my head around this? Whoa, so now, in this case, basically, we're reflecting this guy. Oh my God, what am I doing? We're reflecting this guy in the line, the grey line. So if I was to reflect this line in the grey line, if I bit enough more than I can chew, I think I would get, my head hurts even thinking about this, because you can tell you just never do this. Yeah, it looks like that. Dear goodness. Something along those lines. Oh, my brain. Is that the reflection? Yeah, that is the reflection. So it's really quite different. It's decreasing, for example. So things are a little bit different. We never think about it. So completely ignore what I've just done if you prefer. We completely live, essentially, especially when we're doing calculus in the world where b is strictly greater than 1. Because those are overwhelmingly the bases that matter most to us.